Hi all, welcome to another video of machine learning. In this video, we are going to see the different error functions in linear regression. So this error function measures how the accuracy of a regression model, that is how well a regression model predicts the target variable. Our goal is to minimize the error to provide model accuracy. So we are going to see different types of errors. The first one is mean absolute error, mean squared error, root mean squared error, mean percentage error and mean absolute percentage error. We can see in detail one by one. First, what is mean absolute error? So mean absolute error, that gives the average absolute difference between actual and predicted values. The actual value is y, the predicted value is y cap. So here we are taking the difference between actual value and the predicted value, taking the absolute value and summing it all. We are taking all the absolute value sum and taking the average. The average absolute value difference between actual and predicted value. Then the next one is mean squared error. So here instead of taking the absolute value, here we are taking the average squared difference. Taking the difference, we are taking the difference between actual and predicted values, then we are squaring it, adding it and taking the average. That is mean squared error. Here the problem is that the unit of error, that also will be squared. If we are doing a house price prediction, the actual value minus the predicted value, that will be amount in rupees. So the unit also will be squared. That's one disadvantage of this mean squared error. So to overcome that disadvantage, we are going to see another error function, that is the root mean squared error. So the square root of mean squared error. We know how to get mean squared error. So root mean squared error, that is square root of mean squared error to bring the error back to its original units. So the unit also will be taken square roots. So it will be again back to the original unit. So it will be more interpretable than the mean squared error. So it will be same as the target variable. Okay. So the next error, that is the mean percentage error. So the mean, you know how to calculate the percentage. We are taking the difference, dividing by the original quantity, multiplying by 100. Taking the difference between actual and predicted, dividing by the original actual value, then multiplying by 100. Then we are adding all these error values we are adding and taking the average. So that is average of percentage error. We are first calculating the percentage error for one actual and predicted value, summing it up to get all the values, then converting it by and we are taking the average, that is average percentage error. And the last one we are going to see is the mean absolute percentage error. So almost same as the previous one. Here the only difference is that we are taking the absolute value of that percentage, average absolute percentage difference. Here we are now taking the absolute value in the case of mean percentage error. The only difference to this is we are taking the absolute value of the percentage, then averaging it. Okay. So these are the 5 errors that we are mainly dealing with in linear regressions. Okay. The next one, another important topic, that is the assumptions we are taking in linear regression. This is actually very important. One of the main assumption is that we are assuming that the relationship between x, the independent variables, and the dependent variable, that is linear. This is one important assumption. Our linear regression model may fail. That is, it can fail when this assumption is no longer valid. In that cases, there are situations we can take the log. We can take logarithmic scale and make that function linear. That also works, but there can be many situations the modeling can fail if the x and y relationships are not linear. That is one important assumption. Then the next important assumption is the residuals are independent. Residual means the errors. Errors are independent. That means if you are plotting, here it's given plot residuals against time or the fitted value. Here we are plotting error with respect to our predicted value. And if there are no pattern, if this shows a random plot, there is no relationship between these errors. If the plot is random, we can say the residuals are independent. And if these residuals follow a particular trend, they are correlated. In this situation also, the linear regression may fail. If they are correlated, the linear regression will fail. If they are not correlated, if they are independent, we can apply linear regression to that model. Okay. That is the second assumption, that is the errors should be independent. There is no correlation among the error values. The next important assumption in linear regression is homoscedasticity, that is the variance of residuals, that is a constant. So we can just visualize it from this graph. So if you are plotting a graph between the predicted value and the error or the residual, we can see the errors should not get systematically larger or smaller as the predicted value changes. As y predicted increases, the error should not change to a much higher or lower extent. That is, the error should approximately remain constant. The variance of residuals, that should be a constant. We have another situation, and this shows the homoscedasticity. And we have another situation, if you plot a graph between the predicted value and the error, there can be situations where the error changes like this. As the y predicted changes, error changes randomly. This is known as heteroscedasticity. Heteroscedasticity. Okay. So in this case, linear regression modeling will not work properly. That means the spread of residual should be evenly distributed without forming a pattern. That is, it should not form a pattern, but should be evenly distributed. And if it's getting larger or smaller as y predicted changes, it leads to heteroscedasticity, where the linear regression model may not work properly. Okay. Then the next one is normality of errors. That is, the residual should be normally distributed. We have seen what is a normal distribution. This is a normal distribution, and the errors should be normally distributed. Then the next important assumption is no multicollinearity among the variables. That is, independent variables should not be highly correlated. What is the meaning of that? If we are having two or more independent variables in a regression, the two or more independent variables models are highly correlated with each other, means the effect of one variable can be predicted from the other. One variable we can predict from the other independent variable, making it difficult to determine the individual impact of each variable on the output, on the dependent variable or the output. That means if we have many independent variables in a model, and if we are able to predict one independent variable from the other, we cannot predict, so it's easy to predict the one independent variable from the other. That means we cannot predict the individual impact of those variables on the output. So that is, if they are collinear, they are correlated, or they have multicollinearity, it will be affecting the modeling. So no multicollinearity should be existing between individual independent variables. So that is another important assumption in linear regression. So we can just go through that just summarize it once again. The assumptions of linear regression: x and y should be linear. The errors should be independent. There should not be any relationship between error. They should not follow a trend. Then homoscedasticity means the error should not get larger or smaller as the predicted value changes. Okay. Then error should be normally distributed, and independent variables should not be correlated. So these are the assumptions in linear regression. The next video we can have a coding session. Okay, thank you.